Hey guys, this is the start of the lecture for chapter 19, which is all about electrochemistry. We're going to talk about how electrons are transferred in chemistry. But before we can do that, we have to kind of be able to count electrons in atoms. And this is actually coming from chapter 8, the first page or so, where redox chemistry is actually introduced. So if you are a little confused about where this came from, that's where you can find it. So the first thing we need to be able to do before we can learn about electrochemistry is learn a little bit more about electrons in elements and what their oxidation numbers are. Oxidation number or oxidation state. They're sort of synonymous terms. So the oxidation number or state just describes the type of ion that's formed or how electrons are shared in covalent bonds, because we know they're not always shared equally. So there's rules for determining oxidation numbers, and an abbreviation that I'll use a lot for oxidation number is ON. So the first rule is that any element in its elemental state has an oxidation number of 0. Okay, so that is going to be things like sodium, pure elemental sodium, like the silver chunks I threw in water and made a little explosion in lab, or magnesium. So metals tend to be monoatomic, but we've also talked about diatomic elements, Hofbrinkel, so hydrogen, oxygen, fluorine, etc. are diatomic in their natural elemental state. Some have even greater numbers, like sulfur in its natural state is S6. It's 6 sulfur atoms bonded together covalently. So any element in its natural state is going to have an oxidation number of 0. Okay, that's rule number 1. For monoatomic ions, the oxidation number equals the charge of the ion. So for an iron ion that has a 2 plus charge, the oxidation number on that iron is 2 plus or plus 2. Chlorine has a 1 minus charge, so the oxidation number is -1. Okay, I'm just going to digress here for a second to point out some, I'll call it chemistry punctuation. So you notice that here I wrote the charge as 2 plus and the oxidation number as plus 2. I might have that backwards, but I do know that in chemistry, when it's an oxidation number, you write the charge on one side, maybe the left side, and when it's an ion charge, you write the charge sign on the other side. And I can never remember which is which, and I mix them up, and I don't really care about that particular sort of quote-unquote punctuation when it comes to chemistry, so I won't hold you to that. If you want to look up in the book what the correct orientation is and master it, go for it. Other chemistry professors might be more insistent on it. I don't care as long as you just get the charge right. I don't care whether the plus goes on the left or the right. But just know that there is an actual etiquette for that if you ever take another chemistry class. Alrighty. Rule number 3, the sum of all the oxidation numbers in a compound must equal the charge of the compound. So, for example, this first one here, lithium chloride, overall this has a 0 charge. But it is an ionic compound made of a metal and a nonmetal, so we know that it's actually made up of lithium ions and chloride ions. All right, so the charge on the lithium ion, or the oxidation number, is just equal to the charge, so it's +1. And the oxidation number of the chlorine is equal to the charge, and it's -1. And you add those two numbers together, they overall equal 0 because the overall charge of lithium chloride is 0. If we have an ion, like hydronium ion, H3O+, the charge needs to add up to the actual charge there, so it needs to add up to a +1 charge. Well, the oxidation numbers on hydrogen are 1, because hydrogen makes a 1 plus charge when it's an ion, and the oxidation charge on oxygen, when it forms an ion, it forms a -2 charge. And so when we add 3 hydrogens at a +1 charge, plus 1 oxygen at a -2 charge, we get a sum of 1, which works because the charge here is +1. So the sum of all those oxidation numbers needs to add up to the charge of the compound or polyatomic ion. All right, rules 4, 5, and 6 are specific to certain elements. So fluorine always has an oxidation number of -1, always, always. Hydrogen almost always has an oxidation number of +1, and oxygen almost always has an oxidation number of -2. So hydrogen and there are some exceptions. So when hydrogen is bonded to a metal, it often has a -1 charge. And when oxygen is found in peroxides or bonded to fluorine, it can have other charges. All right. But my general rule of thumb, of course, in this general chemistry class is to teach you guys the rules, let you know about the exceptions, but I'm not going to test you on the exceptions. So we're not going to do any problems where hydrogen or oxygen has any other charge besides -2 and +1. So for now, just assume they always have those charges, but know in the back of your mind that that's not always true. And in future classes, you may run into some molecules that's a different situation. Okay, so let's work this practice problem here. Determine the ON, the oxidation numbers for all elements in the following compounds. And there's 3 compounds listed here. So let's start with the first one. So we've got hydrogens, and there's a rule about hydrogens, rule number 5. They always have a +1 charge. So each of those hydrogens is going to have a +1 charge. Oxygen also has a rule, specific rule. They're always going to be a -2 charge. So now the question is, what is the charge on the phosphorus? There is no rule that tells us what charge is on phosphorus. It can be different depending on the compound. But according to rule number 2, all the charges have to equal the charge of the overall compound. And this compound adds up to a charge of 0. It has a 0 charge. So basically, if we have 3 hydrogens with a +1 charge, and we have 4 oxygens, O4, with a -2 charge, and we have 1 phosphorus, we'll call it X, all right? We add those up, they should sum to 0, the overall charge. So now we just have to do some algebra and solve for X. So 3 plus -8, or 3 minus 8, equals -X. If I move X to the other side of the equation, it becomes negative. So -5 equals -X, and X equals +5. So in other words, we just solved that the charge of the phosphorus must be +5, or the oxidation number of the phosphorus must be +5. So generally when you have compounds, you know the charge of some parts, and then you have to deduce the charge of other parts. So let's do this a second time with the CO here. Sorry, CO2, the carbon dioxide. So we know that oxygen has a -2 charge. That's rule 6. We don't know any rules about carbon, so that's one we have to deduce. Overall, this compound has a 0 charge. So that means that 2 oxygens with a -2 charge plus 1 carbon, or X, equals 0. So -4 equals -X. So X equals 4. The carbon has an oxidation number of 4. Now we know that this is not an ionic compound. CO2 is a covalent compound. These atoms, the carbons and oxygens, don't actually have charges. But we also know that they're not really sharing electrons equally. Oxygen's an electron hog. It will hog electrons from those carbons. And so that gives it a sort of pseudo charge, if you will. That's why the oxidation number is negative for oxygen, because it's hogging electrons. And that number sort of represents that. So oxidation numbers are not truly necessarily charges, especially when we're talking about covalent compounds. Okay, here's another one. Maybe you pause the video and try this third one yourself, but I will work it right now. So we know there's a rule for oxygen that it always has a -2 charge. And potassium is a metal ion. It always forms a +1 charge. So it's in that rule number 2 for monoatomic ions. And it always has a +1 charge, so we can put a +1 there. It's the chromium that we need to solve for. So just set up a little algebra problem. You may even just be able to do it in your head. But if we want to show the work here, 2 potassiums at a +1 charge, plus 7 oxygens at a -2 charge, plus 2 chromiums, our X, we don't know that one, all need to add up to 0 because the overall charge of this is 0. It's not a charged molecule. So now we just need to solve for X. So 3 minus 14 equals -2X. And, 3 minus 14, sorry, 2. 2 times 1 not 2 plus 1. Okay, so 2 minus 14 is 12. Negative 12 equals negative 2x. Divide both sides by negative 2. And we get x equals 6. So the charge on this chromium is plus 6 on each of those chromiums. There's 2 chromiums. And I keep saying the charge. The oxidation number is plus 6. All right, so it's pretty standard to see oxidation numbers either written just below or just above the elements, each of the elements in a compound. You might just note them there. I like to do them below because charges, like ionic charges, go above. And so writing them above can be confusing. So I like writing them below to sort of distinguish them from ion charges because they're not ion charges, they're oxidation numbers. So the reason we need to be able to track these oxidation numbers is because that's how we're going to be able to identify oxidation and reduction reactions, which we just call for short redox reactions. Stands for reduction, oxidation. They always happen together. So redox reactions just involve transfer of electrons. Just like we had with acids and bases involve transfer of protons, right? An acid loses a proton and a base gains a proton. So similarly here, in oxidation, you lose an electron, and in reduction, you gain an electron. And there is a mnemonic to remember that. There's actually a couple, but this is the one I like to use, oil rig. Oil stands for oxidation is loss, specifically of electrons, and rig stands for reduction is gain of electrons. All right, so that is a little bit counterintuitive, right? Reduction is gain. Sounds like an oxymoron. No, reduction is not gain. Reduction is losing something. But this is why it's called reduction. It's called reduction because when you gain electrons, which are negatively charged, it makes the oxidation number go down. So in reduction, the oxidation number is what is reduced. You gain electrons, but it results in a reduction of the oxidation number. So that's how I try to think of it because that makes more intuitive sense to me. Reduction is gain is something you just have to practice and drill into your head because it just feels very backwards when you're doing it. You'll see when we work some problems. Oxidation is loss of electrons, and so if you're losing electrons and you're losing negative charge, your charge goes up. So in oxidation, the oxidation number goes up. So this is like another way to think of oxidation and reduction. In oxidation, the oxidation number goes up because you're losing electrons, and in reduction, the oxidation number goes down because you're gaining electrons. Okay, so let's work some examples here. We've got 2CH3Cl plus F2 reacts to form 2CH3F plus Cl2. So what we need to do is assign oxidation numbers to everything. And so we've got, of course, with a balanced equation, if you have carbon on one side, you have carbon on the other, and chlorine on one side, chlorine on the other. So these elements show up on both sides of the equation, but we'll see that some of them will have different charges or different oxidation numbers on either side. So let's start assigning oxidation numbers. So I'm going to start with the first rule. Any element in its natural elemental state is going to have an oxidation number of 0. So fluorine, F2, and chlorine, Cl2, in their natural diatomic states have a 0 oxidation number. All right, now we'll move to the compound. So on the reactant side, all right, we've got 3 hydrogens. Each hydrogen has a +1 charge, always. Actually, we'll do all the hydrogens. So over here, +1 charge. So the oxidation number of hydrogen does not change. Nothing is happening to hydrogen in terms of transfer of electrons here. Chlorine is a monoatomic ion. When it forms an ion, it has a -1 charge. So over here, it has a -1 charge. And fluorine also always has a -1 charge. That's rule number 4. Okay, and then carbon is the last one we've got to solve for it here. So if we've got 3 plus and 1 minus, then to have an overall charge of 0, then carbon needs to have a charge of 2. I just did that algebra in my head. Sorry, it has to have a charge of -2. All right, -2 plus -1 is -3, and 3 times +1 is +3. So that's an overall charge of 0. Now on the other side, it's going to be the same thing, -2. Okay, so if we look here, the ones that are changing, so carbon, how do I want to do this? So carbon is -2 and -2, so it is not involved in this transfer of electrons. And hydrogen doesn't change either. Its charge is the same on both sides. So the ones that change are chlorine and fluorine. So if we look at chlorine, chlorine on the reactant side had an oxidation number of -1, and then on the product side, it had an oxidation number of 0. And fluorine on the reactant side had an oxidation number of 0, and on the product side, it had a -1 charge. All right, so I like to start with which one got reduced, which one's oxidation number went down, and that is the fluorine. The oxidation number went down, it was reduced. That means it must have gained electrons to go from 0 to 1. It gained an electron, so it was reduced. So the fluorine is what got reduced in this reaction. And we can say what happened was it gained 1 electron because its charge changed by 1. And on the flip side, the chlorine's oxidation number went up from -1 to 0, which means it got oxidized. And that essentially means that it lost an electron. So basically the chlorine lost an electron and the fluorine then gained it. That's what redox reactions are. Electrons generally are not just like spit out into space, into willingly. If a molecule loses an electron, another molecule is usually there to accept it. And that's why redox reactions are coupled like that, redox. All right, so maybe you want to try this one yourself, but I will work it nonetheless. All right, carbon, solid carbon, natural elemental carbon, that is an oxidation number of 0. It's in its natural elemental state. Diatomic oxygen, also in its natural elemental state, so it will have an oxidation number of 0. Carbon dioxide, this compound, we've got to figure out the charges. So in a compound, we know that oxygen almost always has a negative charge of 2, so we're going to give it a charge of 2. And if there's 2 oxygens at a -2 charge, then in order for this whole thing to have a charge of 0, that carbon needs to have a +4 charge. So there's a total of +4 and -4 to equal 0, which is the charge on that compound. So in the carbon, it went from 0 to +4 charge, or oxidation number, and the oxygen went from 0 to a -2 charge. I always like to find the reduced one first because the question is which thing got oxidized and which got reduced. All right, the one whose charge went down and was reduced is the oxygen. So the oxygen got reduced because the oxidation number went down because it gained electrons. And that means that the other one, the carbon, got oxidized. In other words, and we know that because the oxidation number went up, and it went up because it lost electrons. All right, in this case, the carbon lost 4 electrons, and each oxygen gained 2 electrons. So that's because of the magnitude of those charge changes or differences. Okay, so now we know how to identify redox reactions. So practice that in the textbook and in the sapling homework to make sure that you can correctly label oxidation numbers and identify in a chemical reaction which species is oxidized and which species is reduced. Okay, so once you understand and you can track things becoming oxidized and reduced, we can start talking about electrochemistry. Because electrochemical reactions involve the transfer of electrons, and the transfer of electrons or flow of electrons is what electricity is. And so we can use these chemical reactions to either generate electricity, or we can use electricity to make chemical reactions go. And we call these types of structures that we can build to run these redox reactions, they are called electrochemical cells. All right, and we take basically two containers and we separate them. And so we have an oxidation reaction happening in one and a reduction reaction happening in the other, but we connect the two with a wire so that allows the electrons to flow between the two cells. So really the redox reaction is occurring between these two compartments, but you're separating the two reactants. So you're not putting them in the same reaction container, you're putting them into separate reaction containers and you're connecting them with a wire that electrons can flow across in order to donate or gain and lose and gain these electrons. So we call these things half cells, those different containers, and each one we say contains a half of the reaction or a half reaction. All right, so there's two types of electrochemical cells. The first type are called galvanic or voltaic cells. All right, and these are the ones that generate electricity. They're basically batteries. So a battery is a type of galvanic or voltaic cell. Right? And basically what's happening here is you get these spontaneous redox reactions. So they just happen spontaneously. They go, you don't need a catalyst, you don't need to add heat or anything like that. They just go on their own. Okay? Electrolytic cells are the other ones. Electrolytic cells. These use electricity. So galvanic cells generate electricity. Electrolytic cells use electricity from a galvanic cell, probably from a battery, in order to drive non-spontaneous redox reactions. So we skipped over chapter 18 this semester, which goes over this concept of spontaneous and non-spontaneous reactions. But I'm assuming you know what the word spontaneous means in English. It means the same thing in chemistry. So spontaneous just happens, but non-spontaneous reactions will not happen without some kind of energy input. And so in the case of electrochemistry, they need electrical input in order to go. All right, so let's consider this reaction here. Okay, so we've got zinc. Let's do our oxidation number. So solid zinc in its natural elemental state has an oxidation number of 0. Copper 2+ ion, that's easy. The charge tells us the oxidation number. Zinc 2+, easy. And copper, solid metallic copper, is natural elemental state, so it has a charge of 0. All right, so we can write out these half reactions, which is kind of what I've been doing when I was showing you those redox reactions. So the oxidation half reaction and the reduction half reaction. All right, I always like to start with reduction because I think reduction is reduction of charge. So that's the reduction of the oxidation number. And let's see, zinc went 0 to 2, copper went 2 to 0. So it was the copper that was reduced. So we can write that half reaction out as copper 2+. All right, it was reduced, which means it gains electrons. Reduction is gain, oil rig. So it gained, 2 electrons. And that's why we end up with copper 0, a 0 charge in the copper solid. So this is the half reaction. We're just showing that reduction, the gain of electrons that copper went through. And for zinc, we can do the same thing. Zinc's charge went up. Its oxidation number went up. So we had zinc solid, on the reactant side, and it lost electrons. So electrons that are lost are going to be on the product side of the equation. So we ended up with a zinc ion and 2 free electrons. Those 2 electrons then got picked up by the copper. If we add these 2 reactions together, then these electrons would cancel out, and this is our overall equation if we add those 2 half reactions together. So it's kind of like what we saw when we learned like reaction steps, like reaction mechanisms with kinetics. You can add reactions together to get an overall reaction. So we can separate that oxidation, the loss of electrons, from the reduction, gain of electrons, by writing out these 2 half reactions. And those, in the case of a redox, the case of an electrochemical cell, okay, we could set up an electrochemical cell by separating those 2 half reactions. So this is, I usually do a demo in class of this, which is kind of cool. So, but I can't do it here. Maybe I'll try to find a video of one and send it to you, or a picture, and include it with the notes. Okay, so we could do this reaction all in a single container, a single cell, where we have a cup that contains some zinc ions and copper ions, where we put some salt in there, some salt and water, and then we can have a strip of zinc, solid zinc, that we put in there. Okay, so no, what this is representing, this solid zinc, the metal here represents the zinc, and what we have in solution here is a solution of copper ions, some copper salt that we dissolve in water. All right, and what will happen is the zinc will dissolve to some extent in the water, and you get these zinc ions floating around. But also some of these copper ions will form pure solid copper on this zinc stick. And so you'll end up with a strip of zinc that's plated or covered in copper. All right. If we separate the cells, then we can do it this way. So we can actually generate energy if we take the zinc solid zinc, and the liquid zinc. So we put the solid zinc and some zinc salt here in this cell. And then in the other cell, we put the copper. Actually, let me keep my color coding the same. So here's the zinc side of the equation. We've got a solid strip of zinc, a metal strip of zinc, and we've got a solution of zinc ions made with some salt, zinc salt dissolved in water. And then on the other side, we've got the copper half reaction. So we have a stick of solid copper, and we have copper ions in solution. All right. We have to have a way to connect them. So to do that, we use a wire to connect the two. And because this is going to generate electron flow, it can actually generate electricity that will light up this light bulb here in between. So we can capture that electron flow as electricity when we use a wire for the electrons to flow across. Here we don't get electricity because that electron transfer happens right in this local spot, and so there's no flow of electrons. But by using this wire and separating these half reactions, we get flow of electrons. The zinc gets oxidized, it's losing electrons, and the copper gains those electrons, so they're going in this direction here. All right, this is the oxidation side, and this is the reduction side. The side where oxidation occurs is called the anode, and the side where reduction occurs is called the cathode. And I will attach a picture for you with the notes that I use as my mnemonic to remember this. And it's red cat and ox. So it's a picture of a red cat and an ox. So you can remember that the anode is oxidation and the cathode is where reduction occurs. Okay, this salt bridge here is just necessary because as ions form in solution, this way they can sort of travel between and keep the overall solution charge kind of more neutral. So that just helps this reaction continue to go, because as charge builds up, that redox reaction will stop happening. So the salt bridge is sort of just a necessary feature to keep the whole thing flowing. but the important part is the part that I have labeled here. And we'll stop now.